My talk will be about Roman domination graphs. I think you already know what is it because Ismael Hierro from Spain also had a talk in which he said something about Roman domination. Unfortunately, I couldn't hear his talk, so I will start from the very beginning, from the whole definitions. Okay. So what is a Roman domination? It was defined nearly 20 years ago by some guys from United States, by Cocaine, Dreyer, and Hedetniemi. And they defined first a Roman dominating function to be a function such that it assigns a number 0, 1, or 2 to every vertex of a graph. And in such a way that there is one condition that every vertex U for which 0 is assigned is adjacent to at least one vertex for which 2 is assigned. Note that this condition doesn't say anything about vertices with ones. They appeared in Discrete Mathematics in 2004, and this is an example of a graph, and to its vertices we assigned numbers 0, 1, and 2, and we see that the condition every vertex with 0 is adjacent to a vertex with 2. For example, that vertex with 0 is adjacent to 2. That one is adjacent to 2 vertices with 2's, and the same with that vertex 0 and that vertex. Okay, so this is an example of a Roman dominating function because the condition is fulfilled. Here is another example. Here we have 3 vertices with 0s and 1 vertex with 2. And again, every vertex with 0 is adjacent to a vertex with 2 assigned. We don't care about vertices with 1s. So we see, we can conclude that if we assigned 1 to every vertex of a graph, it is also a Roman dominating function. Okay, so as we see, we can define and find plenty of Roman dominating functions in graphs, in a given graph. And we are interested in the function that has the minimum weight, meaning that we add values of our function for every vertex of our graph. Yeah, it is written here. And then we compare those weights and we choose the function that gives us the smallest total weight. For example, in the first example, the total weight is 6. 2 plus 2 plus 1 plus 1 is 6. So the total weight is 6. Can we do better? The second example we considered also has weight 6. We have 4 1s and 1 2, so it's altogether gives 6. Can we have something less than 6? The answer is yes. We can find a Roman dominating function in this graph of weight 4, and we cannot decrease it to 3 or 2. So the Roman dominating number in this graph is 4 because this is the only possible minimum for this graph to find a Roman dominating function with this weight, the smallest possible weight. Okay. Why is it Roman dominating function? This kind of domination has a rich historical background. Actually, it wasn't defined in the 4th century, as is written here, but some ideas strongly connected to Roman domination appeared then very, very many years ago in the 4th century. Then there was a Roman Empire, Constantine I, and he reorganized the economy by introducing golden coins. He allowed religious tolerance. He built a new capital named Constantinople. Now it is named Istanbul. And he also reorganized army because the army took up to 75% of all the taxes of the Roman Empire. So in what way did he do this? First, he placed armed forces not only on the borders of his empire, but also throughout the whole country. And he decided to do this in such a way that every place in every bigger city, every place in his empire, he divided into one of the three categories. The first one was with mobile and stationary troops, meaning that in those places are at least 2 troops of soldiers. If there is an emergency in a nearby place, the mobile troop could be sent away to defend this place. Okay. Another category are places with only stationary troops, and the stationary troop is just enough to be just one in that place. And also there are places without troops at all, so with no soldiers at all, so like 0. So as you see here, we have again 2, 1, and 0, the same numbers as in the Roman dominating function. And the condition that was meant to be fulfilled was that communities without troops, so those ones with 0, should be neighbored by communities with mobile troops, so those with at least 2 troops of soldiers, so that in case of any attack, they can be defended. Okay, so as you see, the second condition, the first condition says nearly the same as the Roman dominating function, that it assigns 0, 1, or 2. And the second condition, it is about the additional condition that should be fulfilled for the Roman dominating function, that every vertex with 0 should be neighbors to a verset with 2. Okay, but there was something in between. The Roman Empire was the inspiration to write a paper by Ian Stewart. It is a famous British mathematician. He writes books about maths. They are also translated to Polish. I don't know if they are available in your languages, but they are widely read by Polish people in Poland in Polish language. So he wrote an article to Scientific American titled "Defend the Roman Empire," and this paper was an inspiration for the Dreyer-headed Niemi, and so on, for the guys I mentioned on my first slide, to define the Roman domination number and Roman dominating function. So in this model, every vertex in a graph represents a location in the Roman Empire, and a location, a vertex V, is unsecured if no legions are stationed there. So the value of the Roman domination function is 0 there, and secure otherwise. So if there is 1 or 2 troops of soldiers in the place. But an unsecured location can be made secure by sending a troops of soldiers to this place from an adjacent location with 2 troops of soldiers. So it is again our Roman dominating function, the same idea, but expressed in different language, in different words. Okay. Why is it domination? Because I told you that this is Roman domination. So why is it domination? A dominating set, I'm sure you already know it by heart, that it is a dominating set is a set of vertices such that every vertex which is outside the set is adjacent to a vertex of D, and the smallest set of this property is called the domination. Smallest dominating set, its cardinality is called the domination number, and it's denoted by Greek letter gamma. So why is it domination? Because every vertex of a graph has either 1 troop of soldiers, 2 troops of soldiers, or 0. But if there are no troops at soldiers at all, it is adjacent to a vertex with 2 soldiers. It means that the vertices with 1 soldiers or 2 troops of soldiers consist a dominating set in our graph. Yeah? So the Roman dominating set is also a dominating set. Okay. There is a very famous inequality chain, which I would like to tell later. But before I go to these things, I will show you. Okay, if you have a mobile phone or a computer, please go to this page with www.menti.com and enter the code, or you can scan QR code. I will wait for a while for you to do this. Don't worry, it's not an exam, it's just for fun. I'm sure you are listening about domination from 4 or 5 hours. So maybe you are tired, so I prepared something like that for you. Don't worry, it's not a test. If you are ready, you can raise your hand, maybe. Are you ready?
Okay, Joanna, I entered this number in this code. Yes, I'm now in the site of menti.com. And then...
Great. Okay. Maybe like that. Okay.
Enter your name.
Don't worry, it's a very easy quiz. The code is still at the top of the page.
Okay. The site told me get ready to play site. Okay, answer.
Okay, I'm waiting. There are 4 people. Maybe some.
Okay.
Okay. If not, let us move. You can also join somewhere in between. There are 5 questions. Oh, sorry. Okay. What is the domination number of this graph?
2.
Don't say, just write it on your mobile phone or on your device.
Yeah. Okay.
Okay, everyone has voted. The correct answer is obviously 2. The points are regarding who was the first to submit answer. Everybody was correct. Okay, so great. Next question. What is the Roman domination number of this graph? Don't say, just write.
P4.
Joanna, I
Three
can't
again.
open the web page. I received some errors.
You should go to menti.com and write the numbers you see.
I see. This website is black in Russia.
Oh dear. Oh. I didn't know about it. Sorry.
No problem.
Okay. So just maybe do the quiz on a piece of paper and then check answers. The answer is 3.
Yeah.
Because one vertex with we need 2 soldiers in one vertex and then 1 soldiers in the other. Okay. Okay, great. Roman domination number again. Okay. The correct answer is again 3. Do you need to see the example again? Why is it 3?
No.
Oh, okay. Okay. Roman domination number of this graph is twice the domination number. Okay. It is the twice. I will show the, oh, sorry, I cannot, can I? No, I can't see the example again, but this graph had a universal vertex. So we can put 2 soldiers there. And for the domination number, we need 1 vertex. So the answer is yes. Oh, GC, you do everything correctly. And the last question. Roman domination number equal to, we assume that there is at least 1 vertex in the graph. There is only 1 correct answer for this question. Okay. Oh, sorry, I didn't show you. Oh, complete graphs. Yes, complete graphs are the correct answer. So GC won. Great, GC. Okay. Let us go back to the presentation. Okay, so very famous inequality chain that the Roman is saying that the Roman domination number is somewhere between the domination number and twice the domination number. And it is quite fun and interesting case because the lower bound is very easy to obtain and characterized for which graphs we have equality, but it is very difficult to do the same with the upper equality. Okay, so for example, the graph we considered at the very beginning, the Roman domination for this graph is 4. And the domination number is, we can take to the domination number just to those 2 vertices with blue tick. So we see that and we cannot do this with just 1 vertex. So the domination number is 2. So it's 2 times 2. So we see that we have equality. As for this graph, we have equality in the upper bounds. Another example, the Roman domination number, or maybe let us start from the ordinary domination. It is very reasonable to put to the domination number all support vertices. So let us take those 2 vertices, they are supports. And yeah, everything except of Vx and Wa is not dominated. So we need to take at least one vertex of V and X, let's say V, and Wa the same. So we see that the domination number is 4. And maybe. So the domination number is 4. So this is 8. What about the Roman domination? We can put 2 soldiers here, 2 troops of soldiers here, and now V, Y, W, D, and U, of course, are made secure. Z is not secure, so let us put there just 1 troop of soldiers. And X, A, B, and C are still not made secured. So let us put 2 soldiers to Y and 1 to C. So we see that the Roman dominating number is 6. So it is exactly somewhere between the domination number and twice the domination number. And this is the corona of a graph. The domination number is 4. We need to take every leaf, either its neighboring support vertex. So this is 8. And for the Roman domination number, let us put 2 troops here. So then it is reasonable if we put 1 troop of soldier in W, and then maybe 2 troops in Y, and then 1 troop of soldiers in C. So again, the Roman domination number is 6. So it is again somewhere in between 4 and 8. In general, we have equality in the lower bound if and only if a graph is empty, meaning it does not contain any edge. If there is an edge, the domination number decreases by 1, because now vertex, let's say that one dominates its neighbor. So the domination number decreases by 1, but the Roman domination number is still the same, because even if we put 2 troops in that vertex to make secure its neighbor, it is still, the number is still the same. For this example, it is still 12. So that's why it is if and only if there is an edge, the domination number is smaller. So it is very easy to characterize the graphs for which we have equality in the lower bound. But for the upper bound, everything is much more complicated. Okay, in the first paper about the Roman domination number, there was a few propositions. I will show you some of them because they are quite short and they show us some intuition which help us how to understand this Roman domination number and how to work with it. So first, there is no edge joining V2 and V1. Okay, since we have a function that assigns 0, 1, or 2 to every vertex of a graph, we may think about it as like partitioning the set of vertices into 2 partitions. V0 is the set of vertices which have 0 assigned, V1, 1 assigned, and V2 with 2 troops assigned. So yeah, so let us divide our graph into 3 subsets. The set of vertices, this is, let us say, V2, and this is V1, and then this is V0, okay? And there is no edge joining V2 and V1. Suppose that there is an edge joining V2 and V1. What can we do? We can, of course, decrease. We can decrease the weight of the Roman dominating function. We can find a smaller Roman dominating function with smaller weight. How can we do this? It is quite simple because here we have 2 troops. Here is 1 troop. But actually, we don't need any troops at that vertex because it is already made secure by the two troops it is adjacent to. So we can throw this vertex from V1 and instead put it into V0. It is better to put here 0 soldiers. It's more economical. The weight is smaller. Okay, so there is no edge that is joining V2 and V1. Okay, since the first proposition from the previous slide is true, I will denote the sets in the other way. Let's here be V2, here V0, and here at the very end V1, because we don't have edges between V2 and V1. So now they are far away from each other. Okay, the subgraph induced by V1 has maximum degree 1. So suppose it is not true. Suppose that there is a vertex which has 2 or more neighbors in V1. So it looks like that. So every such vertex has assigned ones, meaning that there are soldiers, one troop of soldiers in every such place. But again, we can find, if this is the case, we can find a Roman dominating function with smaller weight. How can we do this? Instead of putting at least 3 ones, we can put just 2 soldiers, 2 troops of soldiers here, and no troops here, and no troops there. And now we decreased from at least 3 to 2. So we again found a Roman dominating function with smaller weight, meaning that the first one was not the best one. Okay, it was not the gamma, the Roman dominating function with weight of gamma r. Okay, every vertex of V0. Again, let me divide those vertices into 3 partitions: V2, V0, V1. Every vertex of V0, so those guys in the middle. Every such vertex is adjacent to at most 2 vertices of V1. So again, suppose that it is not true, that there is a vertex, let's say that's one, that is adjacent to at most 2, so at least 3 vertices. Okay, so that one has 0, and those 3 have 1. So the weight of the subgraph is at least 3, but if this is the case, we can decrease the subgraph, the weight of this subgraph in such a way that we here put 2 troops of soldiers, and here no troops of soldiers at all. So we have 2, the weight is 2 instead of 3. Okay, so again, this must be true, because otherwise we can find the Roman dominating function with smaller weight. And also V2, which is here, can be considered as a dominating set, as the smallest dominating set of V2 union V0. Okay, so because just focus on those 2 sets, V2 and V0. If there is a smaller dominating set among those vertices, let us say maybe those 3 vertices dominate every vertex outside of it, like that maybe, and like that. Okay, so in this case, we can throw away the vertices of V2 and take the soldiers we have put into V2 and put them only into those vertices that consist the smallest dominating set in this induced subgraph. And in this way, we have, again, we can find a smallest Roman dominating function, meaning that the previous one, the first one, was not the optimal. Okay. So now we know quite a lot about the dominating sets and the Roman dominating sets. And now let us move to the maybe not so obvious property of Roman dominating functions. Again, we have the graph induced by V0 and V2. And then every vertex in V2 has at least 2 private neighbors in relative to V2 in H, meaning that, again, V2 is the smallest dominating set in the subgraph induced by V2 and V0. If it has just 1 private neighbor, for example, let's say that vertex private neighbor, so it is connected to this vertex and it dominates. Let us say that it is V, so this, no, it can't be V. Let us say it's X. So if the X is only dominated by V, which is here, and V is not necessary to dominate any other vertex, we can just take those 2 troops from V, and 1 troop of those 2 can go home, can go for a holiday, whatever, and 1 troop we can put into X, and we could, in this way, we have a smallest, better solution for our Roman dominating function. Similarly, if V is its own private neighbor, meaning that V dominates only itself, still we don't have 2 troops at V, 1 is enough. Okay. Graphs with have Roman dominating function equal twice to their domination number are called Roman graphs. So the graphs in which we have equality in the upper bound have its special name, because it's not so straightforward to characterize those graphs. That's why people gave them special name, Roman graphs. So for example, this graph on this picture is Roman. What are other classes of Roman graphs? So there are some paper on this topic. I will show you the easiest one results, what have been done for this topic. For example, paths. So if the number of paths is divisible by 3, then it is Roman. We just take to the dominating set every vertex starting from the second. Okay, and also into those vertices we put 2 troops of soldiers, and yeah, the path is Roman. It's a Roman graph. The Roman dominating function, Roman domination number, is twice the domination number. Similarly, if the path is if the number of vertices of a path is, when divided by 3, gives remainder 2, it's also a Roman path. Again, for the domination number, we put those vertices, let's say every 3rd vertex starting from the second, and here we put just 2 troops of soldiers, and everything is made secure. If the path, when the number of its vertices is divisible by 3 and gives remainder 1, it is not Roman, because if there is not just imagine that we don't have this vertex, then we need to take that vertex to the dominating set, but it is enough to put there just 1 troop of soldiers. So the Roman dominating number is not twice the domination number. Similarly, is the same for cycles. So again, the cycles which the number of vertices is divisible by 3 are Roman. I won't tick the vertices. It's the same as for the paths. Also, when divided by 3, the remainder by is 2. And of course, for the other cycles are not Roman. Complete bipartite graphs. There is additional assumption that there is the minimum of those 2 is not equal to, because then the situation is different. For the domination number, we take 1 vertex from the 1 partition set and 1 from the other partition set. For the Roman dominating number, the same, 2 troops here, 2 troops there is enough, and we cannot do any better. So this graph is Roman. Also, every vertex, every graph with a universal vertex. If there is a vertex connected to every other vertex of a graph, there was also an example of such a graph in the quiz, on Menti quiz. So if there is a universal vertex, then the domination number is 1 and the Roman domination number is 2. So this graph is also Roman. And Michael Henning from South Africa has constructively characterized Roman trees as a family of all-rooted trees. Those trees can be obtained from a star by applying 3 operations. I will show you those operations later. This is a tree, and this tree is Roman. For the domination number, we need 4 vertices, 4 support vertices, and for the Roman domination number, 2 here, 2 here, 2 here. We cannot do any better. If we put 2 troops there, it makes secure 3 vertices here, but those 2 are still not secure. So maybe instead of 2 here, we can put 1 here and 1 here, but still the number is 8 and the domination number is 4. So our tree is Roman. This is just a small example of quite a big family of trees which are Roman. Okay. So is it difficult or easy to determine if a given graph is Roman or not? It appears that it is. It is co-NP hard to determine if a given graph is Roman, even for bipartite graphs. So trees are bipartite and they are characterized which are Roman, which are not. If a graph is complete bipartite graph, it is also done. But in general, even for bipartite graph, it is difficult to say whether a graph is Roman or not. Here is co-NP hard, meaning that it is NP hard to say if a graph is not Roman. Okay, this is the co says that there is it is NP hard for negation, for negating this this statement here. So it's not Roman. I will show you a sketch of the proof of this theorem. So to show that determining whether a graph is Roman or not is difficult, we show that it is at least as difficult another difficult problem, well-known difficult problem. This well-known difficult problem is 3-sat. And we will show that if we can, yeah, you can write on my presentation. If you can, if we could decide in polynomial time whether our bipartite graph is Roman or not, we could solve in a polynomial time the 3-sat problem. Okay, what is the 3-sat problem? First, a literal is a logical variable or its negation. So x is a literal and not x is also a literal. X is a logical variable. And we are given a Boolean expression in a conjunction normal form, for example, like here. And so the 3-sat says that in every bracket, we have 3 literals. For example, here in the first bracket, we have not U1 or U2 or U3. So we have 3 literals in every bracket, and those brackets are connected with conjunction. This is conjunction, and yeah, that's why it is 3. And sat, it is short for satisfiable, meaning is it possible to assign true and false to every our logical variable to make E1 true? So to make E true, and in our example, it is easy to see that U3 is true. U3 is true, is 1. Then both brackets are true, so the whole statement is true. So E1 is satisfiable. For E2, if U1 is true and U3 is true and U2 is true, so if every variable is made true, then E2 is also satisfiable because every bracket contains at least 1 true literal. Okay, so for this problem 3-sat, we have variables, logical variables, and we have clauses brackets here. Okay, so checking whether G is not Roman is at least as difficult as checking if formula E in 3-sat is satisfiable. Okay, so G is not Roman if and only if the formula E is satisfiable. How much time do I have? Okay, so we construct this bipartite graph for every variable, for every logical variable. So if the logical variable is UI, we construct those 5 vertices. One of them is UI and one of them is not UI. Here is prime, meaning that it represents the negation of U1. And we have 3 additional W vertices in the middle. And this graph is bipartite. To dominate this graph, it is reasonable to put our soldiers, to Roman dominate this graph, to UI prime or UI to dominate those W vertices which are here. Okay, for every clause, for every bracket, we just have 1 vertex and we have 2 additional vertices and a B, and the whole construction looks like that. So this construction is made for, this is a part of a graph showing our clause C1, which has not U1. So the vertex C1 is connected to UI prime. Then in the clause we have U2 and U3. So our C1 is connected to U2 and U3. So every closed vertex is connected to every literal vertex it appears inside of it. Okay, every B vertex is adjacent to every U vertex, and A vertex is adjacent to every closed vertex. So here, for example, is C2, here is C3, and so on, so on. Okay, and to see whether this graph is Roman or not, let us first find in this graph the domination number. So for the domination number, it is reasonable to put B. Okay, domination number is to put B because it dominates every U vertex, U and U prime vertex. It is reasonable to take A, okay, because it dominates every C, every closed vertex. And to dominate the W vertices, which are inside, we need at least 1 vertex from every, I don't know, diamond, from every those subgraph created for every variable. So for example, U3, whatever. Here, it doesn't matter which we take, which we don't. So the domination number is 2. 2 is for A and B, plus the number of variables. Let us say that we have M variables. Okay, so this is our domination number. I will write it once more. Okay, so it's 2 plus M. And for the Roman domination number, so we can put 2 troops here to B. Then we can put 2 troops to the literal vertices, but let us first assume that our the formula E is satisfiable, and let us choose the whole every literal that is true in case to make E satisfiable. So if U3 is made true to make this the whole formula satisfiable, let us put there 2 troops, and the same for every variable. If it's true, let us put there 2 troops. It is false in our satisfying application. Yeah, if you put true or false to our variables, if the variable is false to make the whole formula satisfiable, let us put there to U prime, to its negations. Okay. So in this case, since if E is satisfiable, every closed vertex is make made secure by those troops which are in the U vertices, which are here. So it is enough to put just one troop of soldiers into vertex A. So the Roman domination number, Roman, if our E is satisfiable, is 3 plus 2m. If it's not satisfiable, maybe I'll cross it. If it's not satisfiable, the Roman domination number is, it is enough to put there instead of one troop. If it's not possible to dominate every close vertex by the by those vertices ui prime, it is enough to put there 2 troops instead of 1. So it is 4 plus 2m. So if E is not satisfiable, we see that the Roman domination number is twice the domination number, so our graph is Roman. If E is satisfiable, our graph is not Roman. And that's how the proof looks like. I will just show you that for trees, it is not also so easy case and straightforward to characterize all those trees. Actually, in the original paper of Michael Henning, there was a small mistake, and not all trees, Roman trees, could be obtained by his characterization, for example. And I will show you an example of such a tree, but first I will show you very shortly, because I don't have much time, how those trees were characterized. So first I think I have one slide less. Oh dear. There should be also the F*1 family of rooted trees. They looked very similar to that one. They differ by, no, sorry, okay, they are somewhere else. Okay, so we have a family of rooted trees. Every leaf is at distance 2 from the roots. This is the root. Okay, and every leaf is at distance 2 from the root, and but 2 children of the root are strong support vertices. This is strong support vertex, and those 2 are weak support vertices. Okay, so yeah. Okay, and for tree, there was a definition for VS set, VS of T vertices. Those vertices which are not which are support vertices, and if we remove a vertex from the tree, the Roman domination number won't decrease. And in the original paper of Henning, this statement was present in this definition, but it should not be there. It was the mistake I told you previously. So because otherwise we can't obtain all the Roman trees. So for example, that tree has Roman domination number equal 8. This tree is Roman. If we remove that vertex, the Roman domination number decreases to 7. So that vertex does not belong to VS. That vertex also is 7. So it also does not belong to there. This is 8. So that vertex belongs to VS. And so on. Okay, so let T be family of all unlabeled trees that can be obtained from the sequence of trees that T1, so the first tree in our sequence is a star. The star is obviously a Roman tree. A Roman tree, I showed you on the previous slides a star, and as an example of a Roman graph. And every other tree can be obtained recursively from the previous Roman tree by one of 3 operations. One of them is to add another star and an edge. Operation T2 is adding of a tree from a family I didn't show you, F1 star. Okay. Like that or like that. And another operation, the last one, is to add a tree from family F star 2. And this graph, this tree is not possible to obtain this tree by the original definition and original formula to obtain Roman trees. It was found by Bernal and Zuazua. I've already showed you this graph. So to make this characterization true, you just need to throw away that the vertex should be a support vertex. Actually, even though there was the mistake in the definition, the proofs are still correct, because in those proofs, this assumption that V is a support vertex was never used by Michael Henning, so it was just this mistake. But still, as you see, it is not so easy to characterize even Roman trees. So there is still lots of things to do in the topic of Roman graphs, and lots to discover still. Even though it's a difficult problem, it is still very interesting. Okay. Thank you very much.
Okay, thank you, Joanna, for your tag. Very nice. Is there any question, remarks?
Are the private neighborhoods disjoint in G if G is a Roman? That's a very good question. Private neighborhoods, if G is Roman, it's not the case if it's not the case here, because here we can put two troops, and then two troops, and then just one and one. So the neighborhoods are not for those. Yeah, because it's not only the case that in the Roman graphs we don't have the vertices with one troop. We can have vertices with one troop, and that makes it more difficult, I suppose. If there are only two vertices with two troops and no troops at all, then the dominating set can be easily changed to the Roman dominating set, but still we can do something with those vertices with ones troops. We still have it.
Okay. Is there any other question? Okay, if not, please thanks Joanna for your talk. Thank you.
I'm very sorry
so
that the Menti quiz didn't work. Maybe it will work next time.
Okay, thank you.
Thank you very much.
Okay, thank you all of the speakers and participation in this workshop. Hamid, if you have any speak, you can talk to participant. If you let me, I say bye-bye to all of the participants. Thank you.
Okay, thank you very much.
Thank you very
Joanna,
much.
your presentation was so amazing. I really enjoyed it. And thank you very much for accepting our invitation.
Thank you very much for inviting me. It was my first time that I was on a conference so far away. Yeah.
And Professor Ali Khani, thank you very much for your support as a scientific chair during this workshop. And to conclude, I would like to thank you for attending our events. Hope so, and we are looking forward to meeting you in the future. And I wish you all the best and good luck.
Thank you very much.